How much time do I have? 20 minutes?
25?
25, yeah. Yes.
Yeah, we started a little bit late. I hope that's okay with everyone.
Okay. Yeah. Oops. I really didn't. Yes. Right. So my talk is going to be, hopefully I'll introduce myself. I'm Erkan. I'm a PhD student at the Intelligent Data Engineering Lab, which is here at UvA. And my PhD is more on learning patterns from the datasets, patterns that reflect co-occurrences between features of the datasets. And we specifically focus on tabular data. And we do this for two purposes: knowledge discovery, just finding interesting patterns from the data that we didn't know before. And also we do this for interpretable machine learning, so making inferences making inferences in high stakes decision making cases. So for instance, in the medical scenarios, or in the case of financial decisions, or things related to law. So this goes more towards interpretable machine learning as opposed to explainable AI, which is more on having a black box model, making the decision, and then come back to the model to come up with a probabilistic explanation to the decision. But this is rather having the models that are by themselves interpretable. So that's the place of this in the AI landscape, let's say. So this field is also the part of the knowledge discovery that I work on is called association rule mining. It's a 30+ years old field. And the main idea is that, let's say if you have a data set, let's say a table, in this case, table of mushrooms, the columns are the features of the mushroom, and then the rows are each row corresponds to a single mushroom. So the goal is to learn patterns from the data that reflects the co-occurrences between the features. So let's say you have, if cap shape is bell, then poisonous, yes. So if you look at the data, whenever the cap shape is bell, two rows, we always have the poisonous, yes. Or we can have combinations of features. If cap color is brown and poisonous no, then this mushroom has to be in a habitat woods. So these patterns are based on the co-occurrence values of in the data. And we can also have rules that has negations, that has existential quantifiers, disjunctions, etc. But the main case that we focus on is just the basic co-occurrence with conjunctions of feature values. And once we learn these rules from the data, the way we evaluate whether these rules are good or not is basically by going back to the training table and then calculating some statistical quality metrics over the data itself. So one of such methods is called supports, which means what percentage of the time do you see left-hand side and right-hand side together in the data sets? Another one is called the confidence, which is the conditional probability of given cap color brown, what percentage of the time do you also see cap shape convex in the data? So we can have more and more quality metrics that explains the piece of knowledge we extracted from the data sets. And based on the knowledge discovery task, you pick a metric that is more suitable for that task and then optimize for that one, let's say. And now I'm going to show you a method from 1994. This might sound outrageous for LLM people, but this is still today the most commonly used rule mining method in the literature. And the way it works is that you basically go through the table and then count let's say first count how many times each feature value combination occurs in the data. So cap shape bell occurs 2 times. Cap shape convex occurs 5 times. And then you set strict thresholds, say that mean support has to be 50%. And then you eliminate the ones that are below the threshold. And then you go to the next round where you create the combinations of feature values and then repeat the same operation until there are no feature value combinations. So each one of these are called items until there are no item sets that are above the thresholds. And then you basically, let's say this is one of the items that you learned that is above the support threshold. Then you create different rules. Let's say we can say cap shape convex implies cap color brown, but we could also say the other way around. And then we calculate confidence of this rule. And then we set a strict threshold for that as well. And then we find the rules that are, again, above this thresholds. So now there are better algorithms, better data structures, but the main idea is always the same. You extract piece of knowledge, a rule, and then go back to the data sets by when you extract this knowledge, you always have to go back to the data and then count the co-occurrences. So the counting is always there. And so as you can imagine, we have to do this in a combinatorial manner. So we have to look into this feature and then this feature and then combinations and then 3 combinations, 4 combinations, etc. So this is a combinatorial problem. And then this leads to very long execution times, and also the rule explosion problem, which means you end up with a high number of rules that are harder to interpret, harder to make sense of, and also harder to process. And we propose I would argue, a drastically different approach. What we have is that it's a more probabilistic approach. And in this case, we use an autoencoder, which is a neural network architecture that people use for representation learning. What we do is we create a smaller dimensional representation of the initial input data. And then the model learns to reconstruct the original data from the smaller representation. And basically, by doing so, we argue that the model also learns the associations between the features, otherwise it wouldn't be able to reconstruct. And since we do this, so this is called an undercomplete structure. Since we have this undercomplete structure, the model has to use a smaller information than the original data sets to be able to reconstruct. So then it doesn't capture all combinations in the columns, but only the ones that are good enough to be able to do the reconstruction. And then let's say you have this autoencoder, it's trained on the data set, it outputs probability distributions per feature. So I have a vector here, or here I have a vector of 5 digits. Let's say in your table you have 2 columns, odor and class. Again, this is about mushrooms. So I have a vector of 5 digits. These 3 corresponds to the features of odor, and the other corresponds to features of class. What we do is that, let's say if you want to test whether odor being full implies any of the values of class, then you set odor being full 100% probability, meaning that I kind of specify my preferences or my prior knowledge on the data, and then leave the rest with equal probabilities per value, meaning that I don't have any prior knowledge. And then we do a reconstruction. And then if the model is able to, let's say, successfully reconstruct, let's say 92% probability, the class being poisonous. And if this is higher than a threshold, in this case, it's 80%, then we say that odor being full implies class being poisonous. So if certain features helps us successfully reconstruct other features, then the initial ones imply the other ones. So in this case, we completely eliminate the counting operation over the table, and training is done linearly, again, over the table. And basically, this allows us to have much, much smaller rule sets with higher statistical quality. And not to go into too much details, but we evaluated on multiple tables across multiple quality metrics, and we always saw that we have much smaller number of rules, tens of times smaller number of rules that has full coverage over the data, meaning that for each row of the data, you have at least one rule that explains this row. And average quality is also always higher than any other baseline. And then what we have also done is that maybe you learn this very small number of rules. They are maybe statistically good, but maybe they lack in terms of predictive power. Because we do this rule learning for knowledge discovery, finding interesting patterns, but we also do this for interpretable machine learning. So what people do in literature is that you first learn rules. There's an algorithm for learning rules, and then there's an algorithm for building a classifier by selecting a subset of rules and also ordering those rules to, let's say, make a classification. So these 3 algorithms, CBA, BRA, and Corrals, are the ones that select a subset of rules, orders them to make a decision, a classification. So we basically give the rules that we learn, a small subset of rules in comparison to the exhaustive methods, and the set of rules that are learned by the exhaustive methods, basically every possible rule that is there. And then we do a prediction accuracy task, and then we see that even though, let's say in this case, we have, 100 times less rules, we still get equal accuracy, or sometimes slightly better, sometimes slightly less. So with a much, much smaller number of rules, we get equal predictive power. You can interrupt me and ask questions anytime. And then we have a Python package called PyAerial. Basically, you can do this in 3 lines of code, load the data, train the model, extract the rules. That's it.
Can you maybe quickly, so this training process, how exactly does that work? So how do you do, like, I assume you need a labeled data set, or?
It's not about, this is unsupervised. Knowledge discovery is unsupervised.
Okay.
It's all about finding patterns in the data. And what we do is so this is categorical data. It's one-hot encoded. We create a basically we have an encoder and a decoder. We encode data to a smaller representation and then decode it. At the decoder, we have binary cross entropy loss and then softmax afterwards, applied per feature. And then we compare this with the initial data. So we propagate the reconstruction loss to the output of this to the initial data. So it kind of learns to reconstruct itself.
But so you're going from this Mark Odor full thing. I mean, that's not very. Sorry.
That's an inference time.
This is inference time.
Okay.
Yeah.
Yeah. Okay. So
it's already trained.
Okay. Okay.
But you said, if you already know some patterns, you can initialize this test vector with what you already know?
No, this is, so the problem is still combinatorial. I still kind of initialize maybe combinations of 3 test vectors, so we call them test vectors. You can also say props. I create multiple combinations, or maybe whatever I have, whatever hypothesis I have in the data, I create them and then do a one forward pass for all of them at once.
But this hypothesis, it can be wrong, right?
I mean, so again, this is wrong in the sense that, okay, if the probability is lower than the threshold, then I already discount it. So basically what we are doing is, this is to simulate the counting over the table, right?
Okay.
So this probability kind of corresponds to actually as if you have counted the co-occurrences. Yes.
I wonder, and I'm saying this, not really sure whether I fully understand the method, but I wonder, wouldn't that make it also easier to basically compute this for updates? Only if you use the previous method you showed, like from 1994, it seems like you have to run the entire algorithm again if your data set changes, or if you just append a couple of rows, you have to do the whole thing again. Because it could change the whole distribution and which pairs are being thrown out and so on. But with this method, it seems like it's very good if you just add append new rows to your table. You could just
just continue training one more forward pass.
Yeah, exactly.
Yeah.
So is that something that people find useful in practice?
Yeah, I don't know who's using it. I don't know. I hope they do.
Who would typically be using this, like association learning?
Yeah, so now I'm doing a research visit at the medical school at the UMC. I'm trying to convince them to use rule learning for knowledge discovery. So they use it to find, let's say we have one data set on blood count data set, basically that shows the matters in the blood and how they are related to each other or to symptoms of some disease, etc. So we use it for those cases, for instance. Use it.
Oh, sorry. No, go on with that.
Yeah, and all other medical data sets is the one updates, let's say. Yeah.
So this is only for like co-occurrence, right? So there's no like functional dependencies, for example.
I mean, I would say we can also interpret this as a negation rule. For instance, if odor foul does not result in a successful reconstruction of class being edible.
Yeah.
I would say that's also a negation rule, so it doesn't imply. So rules based on the absence of feature values.
Oh yeah.
But I haven't tested it myself. Yeah, cool. I have 3 more projects to present.
Yeah. Keep going.
Okay.
That's what I'm saying.
Lots more. All right, so we tested this against every other popular rule mining library, and it's thousands of times faster. For all the ones that are implemented in Python, for those implemented in C and R, etc., it's still up to 10 times faster. But we can also write the same in R and C. So.
How many features are in the table that you're testing?
In this case, it's up to 300. 300, yeah. But it could be, I have more. I have gene expression analysis data sets that is about 18,000 columns. So that's also works. So the main message is reconstruction success implies associations. If certain features help us reconstruct others, then there's an association between them. And then the next what we have done is that we said, okay, tables don't exist in isolation. My project is funded by a digital twin project, creating digital twin of cyber physical systems. And in those cases, we have a table of sensor data and then a knowledge graph that describes the cyber physical system. So what we do is, let's say this is sensors, and then this knowledge graph shows you where this sensor is placed, the context. What we could also do is to enrich this table with semantics from the knowledge graph, and then learn rules, what we call semantic rules, that are more generalizable than rules over the tables only. For instance, if in this first case, if you learn rules over the tables only, which is just sensor measurements, you get rules that says if sensor 1 measures a value between 18 and 20, then sensor 2 must measure a value between 20 and 22, let's say. But if you also do the semantic enrichment from a knowledge graph, what you could get is that, let's say there is an S1, which is type water pressure sensor, and there's a P1 that is a type. This water pressure sensor is placed inside this pipe. Pipe has this diameter. So what we do right now is basically we describe a certain part of this knowledge graph and then say that whenever you see this holds in your graph, this rule is applicable. So we get rules that are not just applicable to individual features, individual columns, but all more generically applicable to the data in comparison to using the tables only. So then you basically need less and less rules, and these rules have higher support and coverage.
So I'm thinking about like Wikipedia and so on. Okay, so these are they also like infer other constraints or something like you could basically populate constraints in Wikipedia, right? I guess is that the
Yeah, I think mainly it's the idea that, at least in this domain, is the idea that you can now have rules that are applicable in general to a system. Instead of saying this particular pipe and has to be on and this pressure is on, but for all pipes in all these situations it works. So in Wikipedia it could also work, you can imagine, for all actors that you have to have this relation, I can imagine.
Yeah, so it's yeah.
So we also apply this on medical data sets. Let's say you have a blood count measurements, and then you have a knowledge graph that describes the known relations between matters, between diseases, etc. So then you can basically take that as a knowledge graph, known diseases, known relations between matters, and the blood count measurements. So you can also do the semantic enrichment here as well. So it doesn't only apply to cyber physical systems, but also other domains too. But then one downside of this approach is that now we replace the algorithmic method with a probabilistic neural network. That means the model also suffers from lack of data. So if you don't have enough data, for instance, in this case, we tested it on gene expression analysis data sets. So this is a very expensive operation to do the gene expression analysis from individuals. So there is not enough data to train a model. So then what we do is basically we do a transfer learning from a tabular foundation model. So we have tried two different transfer learning methods. One of them is that you pass the table to the tabular foundation model, in this case, TabPFN. You get an embedding, and then you project this embedding to our autoencoder. Let's say use this projection to maybe initialize the weights of our autoencoder. Or what we have also done is that so the autoencoder learns to reconstruct data, but maybe we can add an initial objective, which is going to be learning to reconstruct, plus also semantically align the embeddings, the parameters of the autoencoder with the embeddings from the tabular foundation model. So this is done by using a cosine loss, which is more about taking the direction of the vectors as the criteria rather than the magnitudes. And in machine learning, which this is called semantics. Of course, it has nothing to do with the formal semantics of knowledge graphs, but just to make machine learning people happy, we say semantics. Sure. And then, so basically, if you apply any kind of transfer learning with tabular foundation model, so we basically, maybe I'll just advertise it a bit better. We did it for the first time. We use prior knowledge while doing knowledge discovery. And then this basically increased all the quality metrics much higher. And then what we have realized is that, okay, reconstruction success implies associations. And basically what we have is a model that is conditions certain outcomes on certain other features, right? But then we could also generalize this to different models. So what we have done is that if you have any conditional probabilistic model, that allows you to have the queries of the form P I given X. So any kind of conditional querying over the model. And then we have, so this is a bit formal contribution, but what we have said is basically that if you have this type of model that allows you to do the antecedent validation, this threshold and check that I showed you, let's say using a scoring function. So this model supports probabilistic queries, have a scoring function that allows you to allows you to quantify the probability of having X in the data. And if it also allows you to extract consequence, meaning that if you have once you have this conditional structure, conditioning certain features on others, based on a thresholding, based on the scoring function, then you can apply our methods any such models. So more generalizing this to other models. And then what we have done is that we say that any tabular foundation model with a classification objective out of the box can be used to learn association rules. And this also addresses the low data scenario because tabular foundation models are trained on millions of tables, etc. So what we do is, let's say, given this table, we split it into context and query, as in tabular foundation models, and we fit this into a tabular foundation model. We create this probing metrics, which is the same as the ones that I showed you, odor, foul, etc. And then, but the tabular foundation model predicts feature by feature, right? So I have to split this probing metrics per feature and then make a prediction with the model per feature and then reconstruct them at the end to, again, a full prediction metrics this time, not reconstruction, but prediction. So we predict each feature one by one over this probing metrics and then again apply the same threshold. So this shows that you can learn association rules with tabular foundation models out of the box. And in the case of small tabular data, tabular foundation models yields better results in terms of rule quality and also in terms of predictive power. On larger data sets, their benefit decreases slightly, but still they are better. Yeah, but if you have a larger table, since the current family of tabular foundation models can only do per feature predictions, it could be better to use Arial, our initial autoencoder approach, on larger tables.
Why is that?
Because right now with tabular foundation models we do predictions per feature, right? And tabular foundation model is a big
okay, so for large tables in the sense of number of features.
Yes.
Okay.
Yeah. So our autoencoder only has 2 layers or 3 layers. So it's such a super small model. And it can basically make predictions for all features at once. So that's why it's much faster. And yeah, this basically shows that tabular foundation models can scale to small to medium-sized tables, but not too large tables. And we also have a wrapper around this where you can learn rules from any tabular foundation model. Well, I only implemented TabICL, TabPFN, and TabDPT so far, which is two lines of code. So initialize the model and then give a table in pandas data frame form, and then you can learn rules from that. And this basically means prediction success also implies associations, not just reconstruction. I don't know if that makes sense. And that's all. Okay. More questions? I saw 12 people are on the Zoom meeting. Maybe they have questions. Actually.
So what do you think is the main usage for, like, what do you see as the most significant usage of this?
Right now, what I'm doing is trying to apply this on medical data sets with UMC. Mm-hmm. So I'm developing a user interface for any practitioner, any, let's say, clinical chemist, to upload a tabular data. And then based on the features of the table, I'm going to pick the best model to do knowledge discovery over this table, find interesting features based on the definition of the practitioner. So the main usage is just finding interesting patterns in the data, and in the medical cases, that's where I see the most meaningful results. So I try to apply it to medical data sets right now.
So a classic case, actually kind of a very simple case, because I always think about things very simple, is it used to be they used association rule mining for recommender systems, because you can have very small rules that say, oh, if this person buys this much and this product is available, then display this ad. And people still do those kind of recommender systems because there's much simpler models, right? These these rules are very, very simple models in comparison with a big machine learned model. So this is one of the reasons people like semantic association rule mining. In the medical case, it's the same kind of idea, right? You have all this big data. Can we distill it into a kind of a simple, I don't want to use that word, but I'll use it, causal model, or like a very simple model that we could say, oh, you have a broken arm and I don't do medical stuff, and a runny nose, then this happens, right? So we're looking for much simpler explainable models.
So it's really an alternative to predictive models in a way.
Exactly. And this is all the stuff that people did. Like the reason a lot of this, there's a huge literature on it because it was all before we went like, it's even before like SVMs, right? Like this is the kind of.
Do you think that maybe also that this kind of method could strengthen these predictive models in a way? By constraining or like, I don't know, inferring certain rules that can help maybe constrain.
I know that it's already used in feature selection. So we can already decide which features have an impact on certain class label. And only use those features when building a predictive model. That's one case. I don't know other cases. But this is also a predictive model by itself, as I said.
Super interesting.
Yes.
When you spoke about features, it reminded me what about the different data types? Like, does this work for categorical data only or also numerical?
Yeah. So there's a fundamental difference between categorical rule mining and numerical. In the categorical case, it's all about co-occurrences of values. In the numerical, it's more about finding good intervals or features that leads to a higher rule quality. So then it's more on an optimization problem. Let's say in this feature space, you move a certain direction, change the intervals a little bit, and then calculate the rule quality. So it's more of an optimization problem than a co-occurrence, finding co-occurrences. This is so far only on the co-occurrences.
When you say finding the right intervals, it basically means it's a way of discretizing. And there's a lot of different ways you could do the discretization, and then that in itself is becoming an optimization problem.
So this all works with pre-discretization, but you can also do without pre-discretization, directly learn rules. But then the problem becomes finding the intervals that optimizes the rule quality, rather than, let's say, optimizing information gain or something.
And the TRL models somehow helping to make this this problem go away?
What models?
The table representation learning models, the ones you showed in the
Tabular foundations.
Are they helping with this problem somehow? Because
no, this is still on categorical data.
Okay.
But it's kind of an interesting idea. I don't know what would happen if we tried to do numerical rule mining on this using a tabular foundation.
What is going to be the problem? So because you have to change the problem completely.
Maybe we have time for one more question. No.
Yeah, it's a bit of a technical question. When you explain that you like the way you train your autoencoder, you said something to okay, that works because these values depend on each other, so they can be compressed into a smaller space. But let's assume you have a lot of features, but maybe there's only one rule, like one dependency in there. Isn't that like a way that this can be lost because it's so busy trying to reconstruct all of those features that are not dependent on each other, that the one that actually has a rule gets lost in the reconstruction process? Does it make sense?
Or it could be the other way around. If there are so many dependencies, and then it just maybe tries to optimize for a couple. I guess that's more on the question of, because in my experiments, what I also saw that if you, let's say, compress more, then you get rules of more higher association strength. If you compress less, then you get many more rules that are maybe lower in support or something.
But is it a parameter you have in your library that can be adjusted to say?
Yes.
Okay. Nice.
Right. Maybe. Thanks, Erkan. All right. We have drinks at Polder. So for those who want to join, let's go.